Hey guys, Punk here. I'm going to do a quick video on the regulator test. My thoughts on the regulator test, and then we'll get into some really technical stuff. So after I talk about just my thoughts here, if you don't want to learn a bunch of math, then just turn the video off. My two thoughts on the regulator test. Number one, all the regs did fine, except with the notable exception of the PMI reg and the myth reg. I think 20 or 40 psi change in output pressure between 1,000 and 3,000 psi is adequate. And I think a creep of 10 or 20 psi is adequate as well. The only two real failures I saw here was the PMI, which creeped over 100 psi, and then the myth, which just simply was not consistent in output pressure. It makes the input-output curve basically meaningless because the gun has, or the regulator has so much steady-state error. So, that was with used and freshly cleaned regs on all accounts. So, yeah. Those are my initial thoughts. Now, if you want to listen in on why I think that the myth did so poorly in terms of steady-state error, and why I think the PMI reg did so poorly in terms of creep, and you're willing to put up with some math, stay tuned. Otherwise, close it now. All right. So, kinematically, we have a basic regulator. It consists of a mass, which is a piston of some type, and then we have a spring on one side and a damper on both sides. Now this damper is going to be the fluid resistance to moving this mass. Alright, so that's going to change depending on the pressures on there. So that's what makes reg design hard. The spring is easy because we can model springs with Hooke's law very easily. So what we do is we basically take this diagram, which is the regulator, and then we write F equals ma for this equation, or for this situation. So F, which is the force on the mass, equals the mass times the acceleration, which is the second derivative of the position. So position is x. So this dampers are related to the second derivative, and wait, son of a bitch, other way. Anyway, so we write F equals ma, which turns out to be a differential equation. Now, here's where I'm going to have to tell you just the magic happens, because I can't bring you up through 3 semesters of calculus and differential equations to show you how to do this. And then we use a special method in differential equations to solve the differential equation called Laplace transforms. Now, in a Laplace transform, essentially, the second derivative of a function becomes a squared term, the first derivative becomes the function, and then the function itself is just a constant. So what happens is, when we solve this, we get a function called the transfer function, T of S. So we have, when you do Laplace transforms, you always get 1 over, and then you're going to have a coefficient times s squared, that's going to be the second derivative, the acceleration, and then you have a coefficient times the first derivative, that's going to be velocity, and then you have the constant term. Right, so we can use the transfer function to do lots of, ooh, we're tripping out here. We can use the transfer function to do lots of different things. One thing is called a Bode plot, which is a frequency domain issue. So the Bode plot has magnitude of response plotted against frequency of response. So if you guys really want to listen to a study in Bode plots and frequency of response, listen to my little lecture on women's breasts, because they are a perfect example of frequency response. Alright, but that's not for this video. The other thing we can do is we can use standard input functions. Now, there's standard input functions such as the step response, the unit slope response, and other ones. The unit step response essentially breaks rules, and that's why it's not realistic. Essentially, a unit step response goes from 0 at all times before 0. It is 0. And then it goes to 1. Or we can multiply the step function by a number to make it instantly jump at 0. At 0 and any time above 0, it is at whatever number we essentially pick. And that just goes constantly. Another one would be like the slope function. There's a few different things. This is really convenient because it works in the time domain. So we don't have frequency on the x, we have time, which we can measure in seconds, milliseconds, nanoseconds, whatever time we want. Years if we have a really long period. And a lot of times you can build a function out of unit step and unit slope things. But essentially what we have is a unit step problem because it goes from no error signal to whatever PSI the reg wants to output instantly. So when we're in the time domain, we can work in some fun things. So we have the input. We talked about the input. We're going to use a unit step as our input. And then we add that signal, this signal. We subtract off any signal that's coming from the backhand side of the transfer function. And then this is our output. So what we have is a series of controls that are in parallel here that are amps, basically. So you amplify a type of function, which means you basically just multiply it by a number, be that make it bigger or make it smaller. So basically what we're doing is we have an error function, and let's say we're right here on that graph and we want to be here. Basically all this is saying is we take this difference and that's our error. And then if we're making that difference smaller, then that error gets smaller. So the signal into the transfer function always gets smaller, or should always get smaller if we have a stable system. So we have one thing before we move away from the time domain chart here. Now, this would be a model of an electrical version of a regulator, okay? So it has these controls that we can just digitally adjust, which makes things really convenient. Now, it's really easy to think in those terms. Electrical circuits are really nice because we can take all sorts of mechanical systems, fluid systems, thermal systems, and boil them down into electrical systems. And that's essentially what I'm doing here. Realistically, what we're actually doing when we change the mass and the damping and the spring is we're actually just changing the transfer function. So instead of this nice closed loop issue, we're just changing the transfer function. But it's much easier to think in these terms, and it's a lot easier for me to convey to you what's happening if I model it like this for you. So just for all you guys who are as educated or more so educated than me, just to get you off my back, this is how I'm explaining it. This isn't exactly how it really is. We'd have to do the differential equations every single time if we wanted to solve this problem. Just finding a new transfer function every time we change mass, damping, and spring ratios. But it's really easy to think this way. It's easier for me to explain it to people, so we're sticking with it. All right. So we have three types of controls, essentially. Proportional control, which is called P control, I control, which is integral control, and D control, which is derivative control. Okay, next page. So when we have a P control, we're taking that error function. See, here's our desired thing, our step input, and here is, say, the locations of where we are positionally or PSI-wise. So basically, we take the P factor and we times it by this error, and that would be our P factor signal, which then we feed back into here. So most affected by the biggest thing that affects P control is mass. Mass is a huge thing. I control is based on integral control. So essentially, we are taking the integral, the instantaneous integral, which is kind of a crazy idea to think about, but it's an instantaneous integral, which is a unit area between the signal and the desired signal. and then multiplying that by the I factor, and that would give us the error, or the I control signal, which we then add together all in here to subtract off the input. D control is the last one. This is called, both D control and I control are big time affected by springs and dampers, which is what makes them the hard ones usually to fine tune, mechanically at least. When we're dealing with electrical control systems, it's much easier. D control is based on the derivative. So all the derivative cares about is the slope of where we are on this line instantaneously. And so all I control wants to do, the only thing I control wants to do is make those two signals get together. Because as long as those two signals are different, there will be some sort of feedback which will slowly bring it up. All right. Now on D control, all D control cares about is as long as that slope is positive, that signal is being fed back in and a correction signal is being run through the transfer function. So all D control cares about is flattening off, is not changing the signal at steady state. So you can see how I and D control are very, they're opposites of each other, really. And so that brings us to the next thing, which is steady state errors on the step response, which is what we're modeling our regulator with. Again, we're modeling our regulator with which diagram? That kinematics diagram, and then we're putting a step response into it. And then we're looking at it on the time domain. So we're looking at steady state errors to the step response, because that's our model. So what we have here is pounds per square inch would be the y-axis. Now, the step signal is, of course, whatever PSI the reg is demanding, or the gun is demanding. So usually that's about 800 PSI. Then we have time. The red would be our, the PSI being output by the tank. All right? And so what happens is the tank, this signal gets input into this loop as the error, and then it goes to the transfer function, then it gets multiplied out. And so as we get closer and closer here, the error signal gets less and less and less. Eventually, we can have a problem, though, where, and this is mostly due to friction, because proportional control, once we get close enough to these two signals, the difference between those two multiplied by the P factor may not be larger than the friction inherent in the system. And so we will have a steady state error where there's always a little bit of signal being pushed into the transfer function, but it's not big enough to actually move the mass. And so we get a steady state error that is just a displacement off of where we want. Okay? Then another problem we could have is obviously PSI and time again. We can have an unstable system where this thing is flying all over the place. All right, it's bouncing all up and down, and it's just getting a little bit too crazy. Now, so what we needed to do to solve this was add I control, because that will integrate an area here and cause that signal to drop down or go up. We could have steady state error in the opposite direction too. So derivative control solves this problem, because what we want is a nice smooth curve, not this crazy rock and roll crap. And D control, as we learned, just likes to even out that slope. That's all it really cares about. So what's happening on the myth reg is we have the input signal at time before 0. Then we fire the gun, and we have the demand of the gun at whatever regulator. Now, the problem is the myth reg has too much D control. So depending on the instantaneous initial conditions, depending on the friction in there, the damping, the temperature, the viscosity of your fluid, all those tiny things can change just a very minute amount at time 0, and then your D control will get set way off, because a tiny difference in slope at the beginning of the response curve will end up giving you massive steady state error because D-control will dominate. So in the myth, we have too much D-control. On regs that have that bouncing action in the PSI, which things like the Automag regulator has eye control issues. Let's see, other regs that have, there's a nitroduct reg that I've seen the profile of that also has eye control issues. The D control, though, is going to be what's your problem in the myth reg. The reason why it's so inconsistent is it just has too much D control. Ways to fix this? Well, unfortunately, not having the computer model of the myth in front of me, it's pretty hard to run the calculations on how to fix it. Suffice to say, that's what I think their problem is they have too much D control. I have never run into another regulator that has too much D control. In most cases, they have too much eye control, and they tend to overshoot in that case. Or another problem with eye control is it could cause sluggishness in the response curve, because essentially eye control is doing the opposite. It can cause problems in terms of recharge as well. So I hope you guys got at least some of that, but that's a quick run through of basic mechanical control systems, which a regulator is a perfect example of a mechanical control system. And so, again, without having all of the dimensions and all of the viscosities and all of those fluid models in front of me, I can't really do the math in particular for each of these things. But this would be the mathematical model. You can diagnose problems using this model, just like I did with the myth and with the other regs. Now, eye control, another problem with eye control is it can cause creep, and that's what's going on with the PMI regulator. Is there's too much eye control. It just brings it almost makes the signal unstable. And that would be another problem there. Proportional control is probably going to be your biggest control system when it comes to recharge, and that's going to be dependent a lot on mass and then the flow rate of the fluid, the dampers. The spring is pretty much an instantaneous device, so the flow rate is the dampers, and then the amount of mass that they're pushing around is another damper that's going to affect recharge. So, anyway, I hope that gives you something to look at, and maybe you can watch it 2 or 3 times and figure it out. But that's what I think is going on in the reg test, and I hope the new version of the myth fixes its eye control issues, but suffice it to say, I don't have high hopes for that. Anyway, talk to you guys later.